Hello and welcome back. This will be a short session on a single topic, and that is idempotence. We'll talk about idempotent elements and operations and the axioms that arise from idempotence. We'll start by defining another type of special element that we may encounter in a set. And again, we will consider an arbitrary binary operation O times that maps ordered pairs in x squared, the Cartesian product of the set X, back to single elements in the set X. An operation is a function that's closed on all elements of the set, so it's defined on all ordered pairs of inputs resulting from x squared. Now we can go ahead and define an element x is idempotent with respect to the operation O times if x O times x returns that same element x. And if this holds true for all elements lowercase x in this set, uppercase x, then the operation is said to be idempotent. Now what I'm showing here is for a binary operation, but the same concept holds true for either a unary or ternary or higher operation. It's the same idea. If it's a unary operation, then O times x would yield x, and so forth. Let's look at some examples, and let's look at specifically at addition and multiplication operations on the set of natural numbers. We'll start with addition, and we will see that there is just a single idempotent element in the set of natural numbers, and that's the 0 element. And that's because 0 plus 0 returns 0, the same element. But it's not true for any other number in the set of natural numbers. 1 plus 1 is 2, and so forth. 2 plus 2 would be 4. None of these work. Now let's try multiplication. In this case, on the set of natural numbers, we'll see that we have two idempotent elements, the numbers 0 and 1. 0 times 0 equals 0, and 1 times 1 equals 1. On the set of natural numbers, we have two elements that are idempotent with respect to multiplication. No other element in the set of natural number is idempotent under multiplication. And we will take a look at some other sets and idempotence in other sets in subsequent slides. Now let's look at idempotent elements on the Boolean domain. We saw that on natural numbers we had two idempotent elements for multiplication, and those were the elements 0 and 1. And on addition we had a single idempotent element, and that was the 0 element. Now in the Boolean domain we had already shown previously that the AND operation is essentially multiplication. In fact, it was the same as multiplication on natural numbers as long as we restrict ourselves to the numbers 0 and 1. And addition was very similar, Boolean addition was very similar to addition on natural numbers. Not quite the same though. Now the Boolean domain only has the numbers 0 and 1, and we saw on multiplication these two were idempotent on natural numbers. So that's interesting because that means Boolean multiplication, or the AND operation, is idempotent since we only have those two elements. Now addition turns out to be idempotent as well, and that's because of that subtle difference in how Boolean addition works. We had shown in detail before that Boolean addition 1 plus 1 equals 1, while on natural numbers 1 plus 1 equals 2. It's that subtle difference that allows idempotence of all the elements in the set for both the AND and OR operation. So in the Boolean domain we have the interesting concept of an idempotent algebra where both the main binary operations are idempotent with respect to all elements in the domain. So we saw idempotent elements and idempotent operations. Let's talk about idempotent functions. Of course, an operation is a function, and we saw a binary operation is idempotent for all x, xo times x equals x. And for a unary, that would be, the equivalent would be o times x equals x, only having one argument. That's the same as saying f of x equals x, and that would be the identity function or the identity operation. But it turns out that the identity function or identity operation is actually a special case of idempotence. It's true, but it's not the most general case. So we can now make a more general definition for, we'll do that for a unary function or operation. We'll say more generally that a unary function is idempotent if f of x equals f of x. So if we apply f of x to the result of f of x and that equals f of x, then that unary function is said to be idempotent. So the identity function is where f of x equals x is a special case of this, and all we have to do to see that the idempotence formulation given here holds is simply substitute, right? So if f of x equals x, we can substitute that in, then f of x equals f of x. So it means that the idempotence formulation that we have given here holds for the case of the identity function. So the identity function f of x equals x implies that this formulation holds true, but the other way around is not true. So idempotence does not imply that the function must be identity. It can be something else as long as f of x equals f of x, right? So f of x equals x, or identity, implies idempotence, but idempotence does not imply identity. It need not be the identity function for the operational function to be idempotent. Now let's look at an example function, a unary function that is idempotent. The function f of x equals ax, and we will show that it's idempotent as long as the element a is idempotent. So let's take a look. Let's say the element a is idempotent under multiplication. That means that a times a, or a squared, equals a. So a equals its square. If we are talking about real numbers, we already know that could be the number 0 or 1. And our function here is f of x equals ax. So simply a times x. Now let's substitute this into our equation for idempotence for a unary function. So we know that f of x must equal f of x. So let's plug it in. F of x here ends up being a times ax. And since a equals its square, that equals ax, and therefore that equals f of x. So this is an idempotent function as long as the element a is idempotent. Now, in real numbers, this is not particularly interesting because we only have the numbers 0 and 1. But this example is actually inspired by projectors in linear algebra. And at some point when we get to that, we'll see that there are matrices that are not just 0 or identity, they're not just 1 or 0, that are idempotent, and the function ax can be an idempotent function in linear algebra without a being 0 or identity. Let's take a quick look at the unary function of negation. We saw that both binary operations on the Boolean domain are idempotent, so we might be inclined to think that negation might be as well. However, this is not the case. So let's try it. In order for a unary function to be idempotent, f of x must equal f of x. And in the case of negation, not x does not equal not x. Therefore, negation is not idempotent, and it is not idempotent on real numbers either. Now let's summarize what we talked about in this session. What we talked about was idempotence. We talked about idempotent elements, operations, and functions. And we saw that in Boolean algebra, both the binary operations are idempotent with respect to all elements in the Boolean domain, and that leads to two identity axioms that we have listed here that we can use in proofs and theorems later on. We did also see that Boolean algebra is a bit of a special case here, that in most number sets the binary operations are not idempotent, at least not with respect to all elements of the set. We did see idempotence, an addition and multiplication for just a few elements in other sets.